work. I should have come in here, tried it, but it's too late now. So let's see. Got all sorts of other crap here. Let's see. Yeah. Okay, let me go back to this thing. Having trouble finding it. Oh, forgot a letter in here. Okay, let's go to this. I'm not subscribed to my own thing apparently. Okay, can anybody find it? Here, go see if you got. That's the channel. Let's see if I can find it. There's a bunch of other people on there, but if you are logged in as yourself, oh geez. Hang on.
It's working. Yeah, you're live right now.
Am I?
Yes, you are.
Okay. Oh, it wants me to connect to the Wi-Fi here. Okay. Okay, well, I'll take your word for it. How much of a delay is there?
It's about 15 seconds.
Oh, 15 seconds. That's a little larger than I'm expecting. That's okay. So, okay, so we got that for you. So if you're, okay, so I'm logged in as myself here and there. So I guess I don't get notifications to myself. So if I was in a different account, it should send you notifications that things are about to start. So if you want to be notified when the thing starts, it, you know, like if I've already got several people in the other class that are in what do you call it? Isolation, quarantine. So they're not showing up. So this way, I don't think this one's as bad, but I think there's a good chance you might get it. There's a good chance I might get it. And if I get it, I won't be here. But let's see, I'm about right here to all the way to the end. So I'm losing part of the board, but I can move it back and get all of it. If you don't mind, do you mind? Let's try that. It's a good use for an old cell phone. Let's see, how far am I? Oh, I got the whole thing. So that's, the other thing is, I don't like to, half the time the computer doesn't work. So I am working with computer services to get around that. I can do that in this room. Because I think, oh my God, there is 2 HDMIs. So I'll be probably getting my own iPad and just cast from it to the thing to get rid of all the computers and all the crap here. So I'll just be depending on text Wi-Fi. So I hope this is dynamics, isn't it? I hope so. Okay. So here's the deal. Okay, so there's a lot of connotations that happen here. So if you just look at this is what they call kinematics, and that's chapter 12. Okay, so this thing is 15, and I think 16. Although I might be wrong. It's either 15 or 16. Okay, let's go backwards one step. since everybody had me last time, you know who I am, so I won't introduce myself, but I will tell you that the book, they forced me to list the current edition. Okay, so I believe it's 14th. However, if you go back to the 10th or 11th and all those, pretty much the material stays the same. So this book dates back to the 70s. In one regard, it's a good book. There are two generally good books in dynamics that are used across the country. And this is one of the two. There's a little bit of difference between each one. It's just the way things are. It's a fairly good book. The guy that teaches, or guy that wrote it, unlike some of the other people, he still owns the copyright. He teaches at what used to be, well, I forget what it used to, now I think it's University of Louisiana at Lafayette. He teaches down there. It's fairly good, but you can go back and pick up an older edition if you wanted to. There's very little reason now for anybody to produce a competing book because it would be hard to enter that market, although there might be a way of doing it. So he updates it every so often. Some of the updates are good. I haven't paid too much of attention to which ones are, but I have had students get the older ones and say, there's no difference between it and the newer one. The problems might be a little bit different shuffled around. All the problems are on the web, so you already know how it looks exactly the same. There's nothing different there. So kinematics deals with the acceleration. Kinetics, kinetics deals with looking at that combined with, this is pretty much mu, that's just a number. So kinetics is more focused on this. But in order to find the forces, you first have to find the acceleration. So in statics, you had some of the forces in the x direction equals 0, and then some of the forces in the y direction equals 0, some of the moments equals 0 about some spot. Now you got something a little different. So you got that, and you got that. And here, I'm not even going to put this, but I guess I could. But I hesitate to do that, but later we'll see what those are. But probably not as much as these do. So if you look at just a simple case, here's a block. And we'll just kind of rely on some of the stuff that you saw in the friction part. So you saw a part where, okay, give me a second. So say it weighed 100 pounds. Well, okay, so let me stick to the SI for the moment. And say instead it was 100 kilograms. So it weighs that many newtons. The reason you know this and this are the same is you sum the forces in the y direction. Now, technically, now you got to write that. But the box, whatever it is, isn't moving up and it isn't moving down. So now you identify this. Before, in the last thing, it was just kind of left. It was just in the book previous, it was just left as a 0. Nobody said much about it. Now it moves. And so now you got this thing where, say you push, I don't know, so mu, say, is, I can multiply times 0.1 pretty easy. So we'll say mu of the surface is kind of lightly, light sandpaper, and it's that. So the force of friction, and I'll even list this as that because it's maximum, the maximum it can resist without starting sliding is that, which is, you found that because this, right? So if you want to look at it from this standpoint, you could say plus, and you could say, we don't know what this is, so we'll call it N. N goes up, the other one goes down. And so you're happy and you say, okay, N is equal to 9810. Then you're fine. But that's something you knew beforehand. Now that you know that, the force of friction, mu times the normal, take that and take that, and you get, 981. So if you put 500 newtons on the thing, nothing's going to happen. And then this won't be done. This is the maximum before it starts cutting loose. So you start pushing and pushing and pushing. You get up to here, you get 981. And then suddenly it says, okay, no longer statics problem. So it's no longer a statics problem. Now what do you do? Well, what do? You say, okay, let's just take it. Say it's 1,000, even 1,000. Now what happens to it? Okay, so now you got some of the forces in the x equal mass times acceleration. And so the maximum this can give you back is 981, and that's all it's going to give you. This is going to give you, I'm sorry, I should put x. This is going to give you 1,000, so 1,000 minus 981, it was 100 kilograms, still 100 kilograms. Before, you had nothing here, but now it's 100 times acceleration x. So I believe if you look at that, you know what, I'll just do that. So I'll say it's, what is that, 20? And so you get, knock that out, and knock that out, and you got a 0.2 is equal to acceleration x. Now the next question is, and this is crucial to recognize, that if you don't change that 1,000 Newton force here, if you don't change that 1,000 Newton force, and it remains constant, then so too does the acceleration. And so, deeply embedded in this chapter 12 is the fact that acceleration is just a constant. And in this case, it's, what did I say, 0.2. Once it becomes a constant, then you start back in this, oh, this is the cold room. Then you start back in this concept where you're saying, okay, it's constant, now what do I do? Well, what is it? Acceleration is equal to this. But if it's a constant, then it's just a number. I'm going to ignore the fact that it's that. I'm just going to say a constant. And then you got, and what you do, so you've seen this somewhere before. So what happens to you is you say T, and I'll say T0 and T1, velocity at T0, velocity at T1. These have to coincide. Since it's constant, you just pull it out, or you can pull it out. You can leave it in, but it doesn't really do anything. And then you get this out of it. So what you're doing is you'll develop relationships for this to the point where you find x equals x naught plus, I guess I should put an x there. In the book, he listed as s, so I'm going to start with s naught plus v naught t plus, what he says is acceleration t squared over 2, whatever that is. This could be x, it could be y, but everything else becomes x or y as well. So if you want to, you can list it like so. And the reason you can is you can go through all these relationships, pull it out, you get, in this particular case, let's do it like this. Leave it as a variable. You have an initial but you don't know how far you want to go. So what you end up with is taking your A out, T minus T0, and then you basically chop it down. Now what he does in the book is he drops this out and he says it's 0. And then he says V0, this is the velocity at 0. You can start your stopwatch whenever you want. If you're running an experiment and two guys are standing at the start line and they're about to have a race, and they're going to here and here's your finish line, nobody really starts the stopwatch and holds the pistol and waits till it gets to 2 seconds and then pulls the trigger and says go. They do them both at the same time. If you do them both at the same time, you're starting the race at time equals 0. These guys are sitting dead still, but they don't have to be. I mean, there could be a case where they're running already, If that's the case, you can control when you hit your timer and when the race starts. So you go through this thing and you realize AT is equal to, anyway, you can work this out. You can come up with the thing there in which you have these two equations. Then if you're sitting here looking at it, somebody may say, well, after delta T of say 5 seconds, how far does it go? And then you could basically put it in here. You could say if the block is sitting dead still, if you're going to start, here's another thing. Where do you want to measure it from? Okay, so if you're putting a ruler down, and say you put the ruler down somewhere, why would you put the ruler like this? And here's your grading. And say, oh, well, the initial position is equal to 2 feet, or 2 meters. Why don't you just take your ruler, move it over to the point where the ruler lines straight up with the starting location. If you do that, this becomes 0. And then you just get the position, you multiply 5 squared, or 25, times the 0.2 divided by 2, and that gives you how far it goes. So it's that simple. That kind of stuff is going to happen. The next thing that's going to happen is, so this is kind of overview. We'll get into problems, and essentially all I'm going to do is walk in the classroom and start working problems. I hope, but doubt, by next time I'm going to be able to cast to that. It'll probably take a week to get this resolved. They wanted to charge the department $500 or $600. It's only going to cost like $20, so I'll do it myself maybe. So in chapter 12, what happens, you start with stuff like that. Then you start doing multibody problems. Here's a typical case of one. Okay, I'll just say it's terrible drawing, but it's just glued there. And this is going up an incline. So if you think about it, you've got a block A and you've got a block B. Before, things were set so they were static, nothing was moving. In this particular case, things could move. So what you'll have to have is a coordinate system over here. So you could call this SA and have a coordinate system over here, SB, and we'll work out the details because you already know how to do the distance of the ropes. You'll do sum of the forces along the A equals mass times acceleration of the A. And then you'll have another problem over here, sum of the forces of B, mass times acceleration of B. So again, before you were just saying if A moved down so many feet, B moved this way. And how far did it move? Now you're saying they're actually going to move after 5 seconds, say, how far did this one move down and how far did this one move up? And so what we'll do is we'll do problems like that. Then there's going to be those old standards, projectile motion. Somebody shoots a cannon, it does like that. You've done that in physics too, didn't you? No, I'm sorry, physics 1. Did y'all do that? Okay. Really, there's not much different here, except now they have a couple other things, like football player is disoriented, throws the football, but instead he throws it into the stands. Okay, how far did it go? And it turns out, just laying the baseline for you, all this is a parabola. If you just set up an X, I guess that's a good enough Y. I mean, set up an X, here's a Y, you can come up, it is true, you will get, oops, if this is where he started, Y naught equals 0. If this is where my coordinate starts and this is where he, so what I'm saying is, this is 0, and that's 0. There is no acceleration, there's no gravity pulling this way. Gravity is only pulling this way. So you're stuck, that's it. That's all you got there. What you have here, gravity is pulling you back towards the earth. So if you launch the thing this way, that's positive. It's going up for a while. Gravity will eventually, given that this time goes far enough, it'll stop that thing at the top and start returning it back to Earth. Turns out all you have to do is you have to look at this one and say t is equal to x over vx naught. Stick it back in here, and then you have something interesting. Here, you had y as a function of time. Now, you have y as a function of x. Stick that in. Sorry for my bad handwriting. I guess it's not handwriting, it's board writing. Over 2. Now it becomes that. That's all it is. Okay, so you could plug, if you can figure out this and that, which actually you should be, and that, given a certain place, move out here 5 meters, say, you can figure out what y is. Then you can move out here 10 meters and you can figure out what y is. So essentially you put that in here. Now you got this. Okay, rewrite that because it's getting clustered, or, confusing here. All that is y is equal to ax plus b. Doesn't matter what it is, all these problems are basically the same way. The set is just the same. So, what is A? Well, what is B? If you put in x equals 0, that's going to be B, that distance. So it might be, I'm just going to make this up, maybe it's minus 10 foot, or I guess that was in meters. So maybe it's minus 10 meters. So you got that. What is A? It's just the slope. So somehow that'll be given to you. Let's just make it up. Say it's a 4 by 3. So the rise over the run gives you 0.75. X minus 10. That's the stands he's thrown into. Guess what you do now? You set this equal to that, and what you're going to get is you're back in math, and you're going to get this. Hang on. You're going to get 2 solutions, one right there and one right there. And that's it. That's all there is. And basically, you don't want to pick that one because it's going to be a negative something. And so you want to pick the one over there. And that's the... So the thing is he's going to give you a lot of different problems. There'll be a ski jumper, there'll be a golfer, there'll be this. There's all these different types of problems. They all function exactly the same way. You figure out the slope, you figure out the intercept, you figure out the starting x and the starting y velocity. You're going to use g based on what coordinate system. Whether you're, 9.81 or maybe 32.2 or 174 or whatever, depending on where you're at. And that's it. That's all these problems. They look different. They're not different. So you go through that. Then we're going to go through what is, chapter 12 is very long. He starts with motion along one line. Then he goes to motion along an X and a Y. Then from there, he goes into parabolic stuff. And then from there, he goes into polar. Now, polar will make your head swim. And I'll give you a layout of what polar is. Polar is actually, I think, kind of cool. But some people don't think so. And I'll just try to lay it out for you. If you have a vector, say R, out to some point, I don't know, whatever the dot, then you can represent it two ways, X and a Y. And you can say the R vector is equal to whatever that distance X is, plus whatever that distance Y is, times J. Now here's the bizarre thing. Okay, so that's obviously Cartesian, or XY coordinates. The bizarre thing is this. Now, in this book, he uses this. In other books, they may use this. I like this better, but we're using this book, so we're going to use that. So what the crap is that? We know what that is and know what that is. That's a little base vector that sits here like this. It sits here like this. What is that? Well, in polar coordinates, they like to have a vector that shoots out here. Its length is 1. It's called, because of that, it's called the base vector. Just like I or J, except, okay, well, you have to have another one that accompanies it. Except I and J don't change. Okay, there's two things that can change in a vector: length and direction. Neither one of these change in length. That is length 1 no matter what. This is this one and this one are length 1. This one does change direction. I should have put this on there too. If you think of it like this, if you go to there, it didn't change lengths, but it did change direction. You go to here, guess what? If your theta is equal to 0, if theta is equal to 0, then UR and U theta is equal to what? What's UR equal to? It's just equal to I, isn't it? So this is a weird case. But this vector is such that it has to be able to be moved. Then what happens to him is he goes to this thing. He says, okay, if I want to find, and we're going to do this more, if I want to find velocity, it has to be this, right? Well, this one's going to behave different than that one. Why? Because this does change with respect to time. In other words, if you're doing dr dt, where you're doing this, di dt doesn't change at all. There's no change in it. This does change. So how do you manage that? Now in the book he does some weird stuff where he draws this vector and that vector and this vector and this vector, and then he argues, oh, okay, this is the answer. And I think that's a crock of crap. So to me, it turns out you can figure this out, and I'll kind of delay and do that later, but it's based upon the fact that, hang on, this distance is that, and this distance is that. So this means if I wanted to relate UR back to a vector I and J, I can. I can do this. I can say the UR vector is equal to something really weird. If the UR vector is a length 1, it pokes out here, length 1, it turns out now, if I'm going to take a time derivative of this vector, I know this remains fixed. I know that remains fixed. Does that remain fixed? No, it doesn't, because theta could move. So that means you take a derivative of theta, derivative of cosine, you get minus sine theta. That looks like a, but that's supposed to be a theta. And believe it or not, you stare at that a minute and you realize, hey, wait a minute, that looks an awful lot like that one. And so it turns out that it is. You basically find out that this vector is a time derivative. The time derivative of this one is related to that one. The time derivative of this one is related to that one. And we'll show that more. But the key is, this is a function of time. This is not a function of time. And therefore, if you start taking derivative of these base vectors, nothing happens. So nobody ever talks about it. It's just not even part of the deal. And so polar coordinates are caught with this, but once you understand that, you're like, oh, I get it. And so I'll try to go through that. And it seems like it's hard, but it's actually not if you just sort of look at it real precisely. So we'll go there. Then what we find out is from polar coordinates, we develop a velocity relationship and an acceleration relationship. It turns out, I'll show you later, that you remember this v squared over r kind of thing? Now, it could have been r, it could have been, it was basically, if you take your car in the parking lot and you just go circles and circles like this, and it's like, I'm making stuff up, so it's 50 feet. And you're going, 20 feet per second. Now, 150 feet per second is, I think, about 100 miles an hour, approximately. So let's just go ahead and say you're going 100 feet per second. That's pretty fast. So then the question is, what's your acceleration? Well, before, you did this in physics 1, right? Where you did that squared and then stuck it over the distance, so you're going around the square. That'll tell you your centrifugal acceleration. Now it turns out that polar coordinates comes up with exactly that same term, but it's written slightly different. And the reason it's written different is this, is if you look at this, okay, so this is written in like feet per second, right? So if you have a disk, which is essentially what this is, that's spinning, and you want to know the velocity, but instead you know theta dot, how do you find that out? And it turns out it's this, omega, where this is defined as theta dot. Now, you're in polar coordinates now, so you're looking at that and you're thinking, oh, wow, cool. But you can turn around and put this in here, and you can get the same, I'll show you that polar coordinates gives you the same exact relationship as that. They're not any different. No difference. So instead of being a new topic that you got to figure out, it's the same topic. It's just that the terms look a little different. And I'll try to relate that so it basically sets it in your mind. There's certain advantages to both. Let me tell you what the advantages to each one is. I'll give you an example. Guy comes down a ski slope and say he's going to do this and launch himself, okay? So as he comes down here, he wants to know, is it going to break his legs? Is it going to be such a tight turn that he doesn't have the strength to hold himself up? I don't know if you've ever done that, but if you've ever done that, you can have that experience. So what happens is you pick a spot, you come back here, you take the tangent of this, and you can find the radius of curvature. Now it turns out, and he'll have this equation where he shows this, the curvature distance is a function of where you are on there. unless you're going exactly in a circle. If you're going exactly in a circle, you might as well use polar coordinates. If you're not going in a circle and you're coming down this, this thing is y is of x, some sort of function that he has here. You can take two derivatives of this and put it in an equation to determine this distance. So as you're going here, the radius is like out there at an infinity. It's basically, there is no curvature here. Then suddenly he starts feeling it, and he feels it more and more. And so this changes based upon where the skier sits here. Sits here, he doesn't have any centrifugal acceleration. Sits out here, it grows a little bit. You could actually do this, and then your radius of curvature right there. Of course, you wouldn't want to do this, but you could do it in a Hot Wheels car. So the Hot Wheel car comes down, and then it's basically having a lot of centrifugal acceleration to push it down on the track. That's what's keeping it on the track. Otherwise, if you just do this in your Hot Wheel car, they fall off the top because there's not enough centrifugal acceleration. They're not going fast enough. You've done that. Did you have Hot Wheels when you were a kid? Everybody did, didn't they? So the centrifugal acceleration is what keeps the Hot Wheels car attached to the track, so it doesn't fall off. So as it gets higher, if you did this, try this with your Hot Wheels car. Go like this, and then see how long it stays on the track. It's going to fall off somewhere right here. There's no curvature. There's nothing to hold it on that track. So it turns out the V squared over rho or R, whatever. What did y'all use in physics? Rho or R? Or did y'all even, was there anything that, they had to use something, so there was that distance. But in any case, that type of problem works great here. For problems that are associated with rotating machinery, or something that, like, for example, your car has this with a piston on it. Unless this breaks away, unless it breaks, the distance from here to here remains the same. So in fact, you can use this on this, but it turns out polar coordinates, what do you see on your, everybody has them now. You have a speedometer here and you have a tachometer here, RPMs. So if you're looking at revolutions per minute, say whatever number that is that you're reading off. 2 pi radians every revolution. You want to get rid of minutes. And so what do you have is 1 minute equals 60 seconds. So out of this becomes another number, number 2, that's number 1. And now it's going to be, oh, sorry, I was getting rid of this and that, and this and this. So you've got 2 radians per second. That is what you use in the equation. So you can easily change from RPMs to radians per second. And then you can do, theta dot. That's what that is. So if you come up, that would be number 2. So that's the rotational speed. Now we'll find out when we get to the next chapter after that, they rename it. Not too much on difference than this. One term has a derivative in it. You decide, I don't like to keep talking about x dot, so I'd like to rename it to something without a dot. So I'll call it v, I'll call it velocity. Have a theta dot, you get tired of talking theta dot to each other, and you start saying, oh, I'll just call it omega. So they just rename it. That's all it is. When you're talking about this being distance, and then you said, well, ds dt, I can't keep talking about that, but so I'll just call it velocity. And then I'll say, so they're replacing a derivative term with something that doesn't have a derivative, just as a symbol. That's all it is, acceleration. They just happen to use the word acceleration and A velocity in V, you know. But you can just as easily acceleration of, you know, K or something. You could use that symbol. It just doesn't make sense when you're picking it up. You might as well use the V for velocity and A for acceleration. So it turns out you're doing polar, when we get to this point, you'll be able to, this is in chapter, I believe it is 15 or 16, you'll be able to say, I got this going 1700 RPM. What's the acceleration back here of the piston? Why do you want to know the acceleration? Because really what you want to know is something breaks. It doesn't break because acceleration, breaks because of force. Put too much force on it, something's going to break. So you want to go through the accelerations, learn how to do all those, then you come back and you start doing the forces after that. So that's why I do kinematics and go through all that, and then I go through the kinetics. They're supposed to be an I, but it's too late. Then, when we get through those two, so I go to chapter 12, I believe it's 16, then I go back to 13, and then 14. The two other topics that happen in this course that are quite interesting is energy. Energy, you know, you have seen this, haven't you? MGH, you know, what's the other one? 1/2 KX or delta or whatever squared, whatever you want to call this. So we do energy. It turns out energy is a lot more powerful than most people think, because you can use this to solve problems that if you did in a traditional sense would be literally not necessarily impossible, but be impractical to solve. And energy methods will work fine with it. Then the next thing we do after that is we essentially go play golf, so to speak, or pool, or something where we do impact. Now you did this. Did you do the old classical physics problem where bullet got shot into the block and stayed in it, and then it swung and stuff like that? Where you did that? Did you do that? So that's the, let's see. Okay, so this goes back to, and I'll take this time to go back to it. So you've seen that, right? Well, you know, it's kind of like this. What is it? Okay, so that's easy. People understand that. So they look at it's E, M, and C squared. Okay, I get that. Okay, F is equal to MA. I get that. But actually, the equation is this. Why isn't that popularized over that? Because that's the actual equation. And the reason that's not popularized is because for him to understand that, they'd have to take calculus. So take all the population, I'm just making this part up, this is completely fabricated. This might be the population that understands calculus, so everybody else looks at this and says, I don't know what that is. And this, so you got to take this and make it general so the general population can see it. The reason you need to do that is because you need to draw people through this and have a reason to draw people this direction into the realm where you need to know some of the calculus. It gets deeper than that over here. It's not even unspeakable here because it's not even that. It's the population, and there's a certain form of calculation that you need to do in order to do this one. That's even a smaller group of the population. So that's it in a nutshell. And there's some sort of, low battery. What does that mean? Oh no, I got stuck. Oh, I don't know whether this continued or not, but I do have a